Since the dawn of civilization, we have been asking the same question. How did it all come about? We look at the stars, at tiny atoms, at ourselves, and everywhere we see amazing order. But why is this order exactly as it is? And does the universe essentially have a single set of instructions by which it operates? Modern physics has achieved incredible success, but oddly enough, we still cannot see the whole picture. We have divided the world into two parts and written our own ingenious but incompatible instructions for each. General relativity. This theory describes the big stuff: gravity, planets, stars, galaxies, and the structure of the universe as a whole. It works perfectly as long as we are dealing with objects larger than atoms. Quantum mechanics. This theory describes the small stuff: atoms, electrons, quarks, and all fundamental particles. It explains chemistry, light, and almost everything that is not related to gravity. The problem arises when these two sets of instructions need to be applied to the same place. For example, at the center of a black hole, or at the moment of the Big Bang, when all matter was incredibly dense and small. Both gravity and quantum effects are important there. They simply do not work together. Attempting to combine them leads to meaningless mathematical infinities. To unravel the mystery of the origin of the universe, we need a theory of everything, a single, elegant law that includes gravity, quanta, and all particles, explaining them from one simple principle. And it is against this backdrop that string theory emerged. To understand why it is so important for the origin of the universe, we must first understand its most important, simplest, and most radical idea. The main idea is that there are no points. We were taught that all elementary particles, electrons, quarks, photons, and so on, are tiny indivisible points. Physics describes them as objects without any size. String theory proposes to completely change this view. All these particles are, in fact, not points, but incredibly small vibrating threads of pure energy that look like strings or loops. They are so small that even the most powerful particle accelerator cannot see them. If we compare atoms to our solar system, a string would be smaller than an atom by the same amount that an atom is smaller than the solar system. We see particles as points only because our instruments cannot see their structure. Now here's the interesting part. How can the same string give rise to an electron, a quark, and a particle of light? Imagine that the universe is a huge musical instrument, and these strings are its strings, in the sense of the strings of an instrument. How the string vibrates, fast or slow, strong or weak, determines what note it plays. Different notes, different particles. If the string vibrates in one way, we see it as an electron carrying an electric charge. If the string vibrates in another way, we see it as a photon. If the string vibrates in a third, very special way, we see it as a graviton, a hypothetical particle that carries the force of gravity. In simple terms, all the particles that make up absolutely everything in the universe are simply different modes of vibration of the same fundamental object, the cosmic string. This is where its incredible power lies. It unifies everything we know about matter and forces into one elegant concept. Now that we know that everything is made up of vibrating strings, we can understand why string theory so brilliantly solves the biggest problem in modern physics: how to unite gravity and quantum mechanics. As mentioned earlier, our two best theories, Einstein's for the large and quantum mechanics for the small, disagree in extreme conditions. Quantum mechanics asserts that all forces, electromagnetism, nuclear forces, are carried by particles. For example, a photon carries light. To include gravity in this quantum family, we need our own particle, the graviton. If scientists try to simply add the graviton as a point to quantum equations, the math breaks down. The very infinities arise meaningless, infinite values that say the theory doesn't work. String theory gets around this problem in a natural way. There is no need to add a graviton. It arises automatically from the very nature of strings. It is not a separate added particle, but simply one of the vibration modes of a universal string. A certain closed loop of a string, vibrating at a certain frequency, has exactly the properties needed for a graviton, a particle that carries gravitational force. But why does a string, unlike a point particle, not cause infinities? Imagine that you are trying to precisely determine the location of two colliding points in spacetime. The more you try to narrow down the location of their collision, the more infinite the results become. Since strings are incredibly small and long, they smooth out the sharp corners of space and time. Instead of colliding at a single point, the two strings are smeared out in space. This smoothing removes all the mathematical infinities that were previously problematic. It turns out that string theory is the only known mathematical structure that naturally and consistently incorporates gravity into the quantum world without destroying all the equations. This is its main and most powerful achievement, making it the leading candidate for a theory of everything and an explanation of the beginning of the universe. In order for string theory to unify gravity and quanta, it puts forward one incredible but necessary condition. Our universe is not four-dimensional. We are used to three dimensions of space, length, width, and height, and one dimension of time. This gives us the familiar four-dimensional world. However, when physicists apply the mathematics of string theory, it simply does not work in four dimensions. In order for the equations to be logically consistent and eliminate those very mathematical infinities, many more dimensions are needed. The theory requires the existence of 10 or even 11 dimensions, depending on the specific version. But where are the other 6 or 7 dimensions? We cannot see them, feel them, or move around in them. String theory explains this by saying that these extra dimensions have not disappeared. They are simply curled up. This process is called compactification, and they have become incredibly tiny, much smaller than strings. Imagine a garden hose. From a distance, it looks like a one-dimensional line, but if you get close, you will see that the hose has two curled-up dimensions, width and thickness, which you can move through if you are small enough, like an ant. According to string theory, the extra dimensions are wrapped up in complex six-dimensional geometric shapes called Calabi-Yau manifolds. They are present at every point in space, but are so small that they remain invisible. The shape and size of these curled-up invisible dimensions are the key to understanding our universe. How these Calabi-Yau manifolds are curled up determines what laws of physics we see in our familiar four dimensions. Here's an example. The shape of the curled-up dimensions determines the mass of all particles. Why is an electron so light and a quark so heavy? The force of gravity and electromagnetism. Why are there three families of matter, quarks and leptons? In simple terms, extra dimensions are the genetic code of the universe. Different ways of curling them up lead to different universes with different laws. And if extra dimensions determine all our laws, then perhaps it was their state at the moment of the Big Bang that caused our universe to look the way it does. String theory is not just a description of particles. It is a whole story about how our universe could have been born. If everything consists of strings, then the moment of the Big Bang itself must also be described by them. Modern cosmology asserts that immediately after the Big Bang, the universe underwent a phase of cosmic inflation. It expanded incredibly quickly in a tiny fraction of a second. This explains why the universe is so uniform and flat. But how does this relate to strings? Physicists need some kind of energy or field that triggered this inflation and then switched off. In string theory, inflation can be triggered by fields associated with extra dimensions. In simple terms, small changes in the shape or size of these tiny curled-up dimensions could have caused enormous pressure, leading to an instantaneous, explosive expansion of space. To make string theory even more powerful, scientists have discovered that there are 5 different but mathematically related versions. All of these versions come together in one big structure called M-theory. This theory requires 11 dimensions and introduces a new object called a brane, from the word membrane. What is a brane? These are multi-dimensional sheets on which strings can live. Our familiar universe may be just one such three-dimensional brane floating in a larger 11-dimensional space. This idea offers a radically new view of the very origin of our universe. What if the Big Bang is not the beginning of time, but simply the most recent event in an infinite cycle? Instead of starting from an infinitely hot singularity, the Big Bang could have been the moment when two parallel branes of our universe collided. The energy from this gigantic collision was the source of all the matter and energy we see today. This model avoids the problem of singularity and gives strings a direct role in the creation and structure of our universe. String theory provides an elegant mechanism for explaining the very beginning of the universe. It does this using the same fundamental building blocks, strings and higher dimensions, that have successfully unified gravity and quantum mechanics. So we have established that string theory offers a new picture of the world, where everything consists of vibrating strands of energy and the universe has many dimensions. But why is it considered the strongest candidate for a theory of everything and an explanation for the origin of the universe, rather than just a beautiful mathematical idea? Here are three main arguments. The first is unsurpassed unity. This is the most compelling argument, which we have already touched upon. String theory is the only mathematically consistent structure known at this time that successfully unifies general relativity with quantum mechanics. In this theory, the graviton, the particle that carries gravity, is not something that needs to be tacked onto the system. It arises automatically as a necessary mode of string vibration. No other quantum theory can do this without breaking down. And because strings have length, they smooth out the sharp corners of space, eliminating the very mathematical infinities that make all other attempts at quantum gravity meaningless. Second, an explanation for the mysteries of black holes. Black holes are extreme objects where the laws of relativity and quantum mechanics intersect. Any successful theory of everything must be able to describe them. Scientist Stephen Hawking showed that black holes have entropy, a measure of disorder, which according to the rules of quantum mechanics means that they must have an internal structure. However, the theory of relativity describes a black hole as a simple point without details. This was a serious contradiction. String theory was able to accurately calculate this Hawking entropy using the very same vibrating strings that are inside a black hole. This was a huge achievement. String theory provided a microscopic explanation for a macroscopic phenomenon, uniting both areas of physics. Third, predictive power. A good scientific theory should not only be correct, but also beautiful and predictive. String theory has the potential to explain the entire structure of the standard model of all known elementary particles and forces. Instead of a multitude of different particles, we need only one equation for string vibration. String theory doesn't just allow for 10 or 11 dimensions, it requires them. This isn't an accidental addition, but a fundamental necessity for its mathematical work. When something is so elegant and necessary at the very core of a theory, it often points to a deep truth. Ultimately, string theory is the most likely explanation for the origin of the universe because it resolves a central conflict in physics and explains extreme phenomena with a single mathematically flawless mechanism, making it the unrivaled candidate for the theory of everything. Like all theories, string theory has a problem. It allows for trillions of possible universes with different laws of physics. This is where it ceases to be just physics and answers the main philosophical question. Everything is not just random. This explanation is closely related to the anthropic principle. Consider the facts. If gravity were slightly stronger or weaker, stars would either burn out too quickly or be unable to form at all. If the mass of an electron differed from the mass of a proton by even a tiny percentage, the chemical bonds necessary for water and life would be impossible. The density of dark energy in our universe is perfectly tuned to allow the universe to expand slowly enough for galaxies to form, but fast enough to prevent it from collapsing. This seems like incredible luck or even a miracle. Why did our universe choose the very laws from the string theory landscape that allowed us to come into being? The theory, with its landscape of trillions of possibilities, offers a simple, albeit controversial, explanation for this luck: the multiverse. If every point in the landscape corresponds to a real universe, then there are a huge number of universes. The anthropic principle is a principle of observation that states, we can only observe those universes in which the existence of observers, that is us, is possible. In simple terms, we cannot see a universe in which gravity is too weak, because stars, planets, and accordingly, we ourselves could not have formed in it. We can only exist in a universe that is perfectly tuned for life, and this is not a miracle, it is a statistical inevitability within the multiverse. String theory, through the concept of the multiverse and landscape, allows us to answer the question of why the laws of physics seem to have been created specifically for us. Not because the universe was created for the sole purpose of giving birth to us, but because our universe is one of trillions where ideal conditions have randomly come together. The existence of such a broad picture of possibilities, naturally arising from the mathematics of string theory, transforms our ideal laws from an incredible coincidence into the expected result of a huge number of attempts. As far as I'm concerned, it's logical. We have discovered that string theory is not just another hypothesis, but the most powerful and mathematically elegant theory of everything. It accomplishes the most difficult task in science. It was the first to unite gravity with quantum mechanics. It claims that all particles are not points, but vibrating strings, and the type of particle depends on its note. It explains how our universe may have originated through cosmic inflation or brand collision, and why it has these particular laws thanks to additional dimensions. Finally, through the concept of the multiverse and the anthropic principle, it gives us a logical explanation of why our universe is perfectly tuned for life, confirming that everything is not just random. Despite all its beauty and logic, string theory has one critical flaw: the lack of direct experimental evidence. We cannot see strings or curled-up dimensions because they are too small. Physicists are, of course, looking for indirect evidence of the existence of extra dimensions. For example, data from the Large Hadron Collider may reveal signs of new, heavier particles whose existence is predicted by the theory. Much of the work involves further study of the theory itself to find unique predictions that could be tested. In general, string theory is not just the best, but practically the only working mathematical structure capable of fulfilling Einstein's dream of a unified theory. That is why, despite the current experimental difficulties, string theory remains the most likely path to a definitive answer.